Newton's law of cooling. The rate of change in the temperature with respect to time is proportional with the difference between the ambient temperature, m, and the temperature at any time, t. So because it's proportional, we write dt equals k times n minus t of t, where k is a constant. So let's solve this problem for t. I want to find the temperature at any time. I want to find the equation of t of t. How do we do that? Well, let's start again with the equation dt equals k times m minus t of t. So I'm just going to write it like that just to simplify my computations here. I notice that this is a separable equation because m, the ambient temperature, is going to be given. It's going to be some constant, 20 degrees, 50 degrees, whatever. So we get t dt over m minus t equals k dt. So now we are ready to integrate. The left-hand side is, as we can see, the derivative of this denominator with respect to time is -1. So I'm going to put this -1 here, and I'm going to multiply by -1 in front, so that the actual operation that we did was multiply by 1. So we get negative ln of absolute value of m minus t equals kt plus some constant. We multiply by -1 and we get ln of absolute value of m minus t equals negative kt minus c. We raise e to each left side and right side, so we get absolute value of m minus t equals e to negative kt minus c. And I'm going to show all the work this time, how we get all the constants. So we get e to negative kt times e to negative c. This is a constant, so I'm going to actually write it out as c e to negative kt. I compress it back into a constant. Now m minus t is going to be plus minus c e to negative kt because of this absolute value, which becomes like if I have absolute value of x equals 3, x can be plus or minus 3. So again, we compress it back into a constant. So m minus t equals c times e to negative kt. So the temperature t at any time is going to be m minus c e to negative kt. And for some initial conditions, we can find k and we can find c. Let's look at this example. The ambient temperature is 20 degrees Celsius, so in a room. The initial temperature of the object that is brought in the room, like a coffee or something hot, is 50 degrees Celsius. After 10 minutes is 40 degrees Celsius, and what's the temperature after 20 minutes? So the temperature at any time t, which we found above in green, is going to be 20 degrees minus c e to negative kt. So c and k are constants. I don't know them just now, but I have some initial conditions. So t of 0 is 20 minus c times e to 0, which is 1, and that is equal to 50 degrees Celsius. So then c is going to be equal to negative 30. So the new t of t is 20 plus 30 e to negative kt. But t of 10 is calculated by replacing t with 10, so negative 10k, and it's given to be 40 degrees. So 30 e to negative 10k equals 20, e to negative 10k equals 2 over 3, negative 10k, I apply ln, equals ln of 2 over 3, so k is negative 1 over 10 ln of 2 over 3. And I'm going to keep the k in this format. So t of t, the temperature of time, or the temperature of the object with respect to time, is 20 plus 30 e to 1 over 10 ln of 2 over 3t. So we solved part A. Part B says find the time so that 20 plus 30 e to 1 over 10 ln of 2 over 3t, it's equal to 25 degrees. So if we solve this equation, we get equals 5, we divide by 30, e to 1 over 10 ln of 2 over 3t equals 5 over 30, so it's 1/6. I apply natural log to both sides, so 1 over 10 ln of 2 over 3t equals ln of 1/6. So t is ln of 1/6 over 1 over 10 ln of 2 over 3, which is, I can move this above, so it's 10 ln of 1 over 6 over ln of 2/3. And if we put this in the calculator, we will get approximately 44.19. So since I didn't specify anywhere in my problem, I'm just going to consider that the time was measured in minutes. So after 44.19 minutes, the temperature is going to be 25 degrees Celsius.